In this lecture, we will discuss how to design a read-only memory and a programmable logic array. We will create an 8x3 read-only memory, but in practice you will build much larger ROMs. We will also create a 3x3 programmable logic array to highlight the differences between these two technologies. A ROM essentially implements the canonical expression of every output variable. In order to implement these canonical expressions, we need to generate all possible minterms with a set of AND gates, and then combine these minterms to create our outputs with OR gates. To create all the minterms, we will first need to make every variable and its complement available. These long wires are called rails. We will connect these rails to AND gates, where the dots at the intersection show where two wires are fused together. To simplify our diagrams, we typically draw these three wires as a single rail with multiple fuses. Then, we implement every minterm with a set of AND gates. With this design, we start with minterm 0 and end with minterm 7. For the next step, we must combine the appropriate minterms together with OR gates to create each output expression. Because we will include only those minterms that output a 1 at least once, we will remove these three minterms that don't appear in our expressions. And this will hopefully simplify our diagram and leave space for the OR gates that will create our outputs. As we did before, we will place dots at the intersection of rails to indicate which minterms are included in each output. ROMs are not minimal circuits, but they are easy to design. Their ease of design makes them ideal for situations where we need to store large amounts of information, or if we want to prototype a large number of combinational circuits. A ROM can provide a quick test to see if we designed a circuit correctly before we do the hard work of minimization. To demonstrate why full circuit minimization is hard, we will discuss the Programmable Logic Array, or PLA. A PLA can be implemented in much the same way as a ROM, except that we want to create a minimal circuit design for several circuits at once. Hence why we describe the size of the PLA according to the number of inputs, rather than the number of addresses. Because we want to create a minimal circuit design, let's redraw our truth table as a set of K-maps. First, we identify all of the essential prime implicants. As you can see, the AB prime implicant will be included in two of the outputs. What may be less obvious is that B prime C and BC prime implicants of F and G cover the same cells as the single prime implicant for the H output. Since we want to minimize the circuit tree for all three circuits simultaneously, we will make H slightly less minimized so that we can have 3 product terms rather than 4 product terms for all 3 expressions. Now that we have our expressions, we will connect the rails of our PLA to implement each product term, and then we will connect these product terms to OR gates to produce our outputs. Based on these examples, you should ideally have seen that ROMs and PLAs are based on similar technologies, but that PLAs implement minimized expressions, while ROMs implement canonical expressions. When you design circuits, you want to choose whichever tool matches your needs better.